So today is a continuation of yesterday's introduction to substitution as a method for solving systems. That's lesson 5.2, and we've talked about how to use the method itself to solve systems that traditionally intersect at one point, and have an ordered pair solution. And what we're going to extend on that topic today is to see how some of these special cases or these special situations, how they appear or what they look like when they come up in the process of the substitution. So we'll work on that, and we'll also practice setting up some word problem types of systems and solve those with substitution as well. So let's get started. Special situations. So you probably at the beginning won't know you have a special situation ahead of you. You're just going to go through the process of substitution like we normally would. So just to do a quick review, we would look at our system and we would look for something that looks like this, where one of our variables is by itself isolated already. It could be X, it could be Y. Doesn't matter which one it is. It doesn't matter if it's the top or the bottom, as long as in one place we have a variable by itself. Okay, so that we have a statement that tells us that that variable is equivalent to some other expression, like 4x minus 2 here. Okay, once we know that, then the next step is to substitute. We're going to say, hey, if y is equivalent to all of that right there, right, 4x minus 2, if y and 4x minus 2 are exactly the same thing, then whenever in the other equation, wherever I see a y, I can insert this into that spot, okay, and replace the y with that 4x minus 2 expression. And that allows us to solve by substitution because it gets rid of the problem of having multiple variables. So I see the y's by itself. I'm like, perfect, I'm ready to go. 4x minus 2 is equivalent. I'm going to insert it right here. So I'm going to recopy this equation. X minus 1/4, but instead of writing a y like they did, I'm now going to insert in that place. I'm going to insert this expression that I know is equivalent to y. So these guys are equal to each other. That's going to go in here. So I'm going to insert that 4x minus 2, and that's equal to 1/2. Okay, so we practiced that in class today, and all I've done is, everything else is the same, x minus 1/4. All I've done is replace the y with this equivalent expression, and then equals 1/2. Everything else is the same. And now it really becomes review. We just simplify and solve. We'll distribute this negative 1/4, sorry. So we'll distribute that, so we'll get x. Negative 1/4 times 4, well, a negative times a positive is a negative, and 1/4 times 4 is actually just 1, so I get negative 1x there. Okay, and then negative 1/4 times a negative 2, well, a negative times a negative is a positive, and 1/4 times 2 is 2/4, or in other words, 1/2. Okay. So we've done the distribution. The next step would be to combine like terms. And then I have two x terms, so I go to combine them. And this is where you realize something's going to happen, because when you go to combine the positive 1x and the negative 1x, they are going to cancel out. X minus x is 0. Okay, so that cancels itself out. Those guys are gone. Okay, so you could write a 0. You could just say, hey, these guys went away. And our variables disappear. And we are left with a statement that just has a 1/2 is equal to a 1/2. If this sounds familiar, it should, because we did these types of problems back when we were solving equations in chapter 3. Oh, sorry, not chapter 3, so chapter 1 and part of chapter 2. And if our variables disappeared on us, we knew that that didn't necessarily mean we had done something wrong. Of course, we'll check our work, but it means we had a special situation. It's exactly the same thing. So if your x's disappear on you, then you know you have a special situation, and that what's important is to learn what's left. Is 1/2 equal to 1/2? That's the question, right? Well, yeah, that's a true statement. That is true. And if it is, then our answer here is infinitely many solutions. So infinitely many solutions. And that's review. We had already done problems like that before. We're just using it in the we're doing them in the context of systems, but we've already done this kind of thing. Okay, let's try one more. So let's look at number 8. In number 8, right away, I can tell that nothing here is isolated. Okay, so, and this can do a little simplifying too, but we'll deal with that in a moment. So I could pick any one of these variables here and go ahead and isolate it so I can proceed. I think I'm going to go with this bottom one. So on this bottom one, I'm going to do myself a favor and clean this up a little bit, distribute that. So when I do that, I get 1/3 x, and then 1/3 times 6 is 6/3, which is just 2. And then I'm going to get y by itself by moving that 1 out of the way. So now I have y equals 1/3 x plus 3. And since that y is by itself now, I can take this expression and I can insert it for y in the other equation. So now that this y is isolated and I know y is equal to 1/3 x plus 3, then I will come to the other equation, and and I'll just write it again, but instead of writing a y, I'm going to insert this expression that I know is the same as y. Okay, so I'm going to take this guy up here, I'm going to copy it again, so it's going to be x minus 3, but instead of doing 3y, I'll open a parentheses, and instead of writing a y here, I'm going to write this expression that I know is equal to y. So that'll be 1/3 x plus 3 in there, and everything else stays the same. This is still equal to 12. So it should still be the same equation, x minus 3. The only thing I'm replacing y with is this 1/3 x plus 3, which I know is equivalent, and then equals 12. Awesome. And now we can solve for x here. So I'll distribute, and the rest of this is review, so we'll just distribute and solve. So if I distribute this -3, x is going to hang out for a moment. -3 times 1/3 x. Well, a positive times a negative stays a negative. 1/3 times 3, well, that's just 1. And I get an x there. And then -3 times +3 is a -9. And then I go to combine my like terms, which are these guys, and I realize that they are exact opposites and they're going to cancel. So x minus x, or 1x minus 1x, either way, that cancels out. And I'm left with just the -9 equals 12. And I know it's a special situation because my x has disappeared and I'm left with nothing but numbers. But again, what's important is to know how to read this so we can make a final decision on our solution, right? So over here we had something that was equal to itself and it was true, and that was infinitely many. Here I have something that says -9 is equal to 12. That makes no sense. That is not true. -9 is not equivalent to 12. These are two different numbers. So that's how we know this is going to be a no solution. If you get a statement that is false and it doesn't make mathematical sense, then you know it's a no solution. So number 8 is a no solution. There it is. Okay, so that's what those special cases look like. Try number 9 and see how it goes. Take a pause, try it on your own, and then replay the video and check your answer. Okay, so check your work here. You already had this guy isolated, the y at the top, so it was pretty much ready to be to start the substitution process. I just copied the bottom equation, 2x plus 4 times, and then I inserted this expression where the y was originally, and then equals 12. Distributed, I get -2x plus 12 when I distribute that 4. And then when I go to combine my like terms, once again, my variables disappear, right? So 2x minus 2x is 0. The variables cancel out, and I'm left with a statement that says that 12 is equal to 12. That's true. Those two things are equivalent. They're exactly the same. And that's how we know that our final answer is infinitely many solutions here. Basically, they're the same line. Okay, so that's what special cases look like when you're doing substitution. Your variables disappear and you decide which of the two special situations it is based on what's left over and whether it's true or it doesn't make sense. Okay? All right, let's go to the word problem here. We've got number 10. It says a video rental company offers a Super Saver plan that includes a monthly membership fee of $10 and charges $2 for every DVD that you borrow. Okay. They also have a Movie Lovers plan that charges $15 per month, but only $1 for every DVD that you borrow or rent. Okay. So we want to write an equation that represents the Super Saver plan. X is the number of DVDs rented and the total cost per month, right? So in fact, Y is really the total, right? Total cost per month. Let's make that change there, make it more clear. So let's talk about the Super Saver. So Super Saver, you pay $10 a month plus they charge you $2 for every DVD that you borrow. So if I were coming up with an equation for that, I would always be paying those $10 every month plus $2 for however many DVDs. Okay, so my cost in total for the month would be this relationship. Every month I would pay $10 plus $2 for every DVD I rent. Okay, this was back when we still rented DVDs. And then that would be our expression for the Super Saver plan. We will do something similar in part B for the Movie Lovers. The Movie Lovers, their total cost is going to be the $15 they have to pay every month and then an additional $1 for every DVD rented. So if we kind of follow the same logic here, every month we pay $15 and then in addition to that, $1 for every DVD rented, and that gives us the total for that month. You know, if I rent 4 DVDs, it's going to be $19, right? I pay $15 for my regular fee and then an extra $1 for every DVD. So there's our two equations. Together, they can be a system. So when it says how many DVDs do you need to rent a month for the cost to be equal, we basically want to know when are these intersecting, when are they the same. Okay, so we'll use substitution for that. It says we want the cost to be equal, so basically we want to know when is this equal to that. So they're both solved for y. So all I have to do is take one of these expressions and ascend it into the other. So if y is 2x plus 10, I can insert that here and basically just say, all right, well, when is this Super Saver plan going to be equal to the Movie Lover plan? Okay, so you're setting them equal to each other, which is the same act as substitution here. If y is equal to this, then where I see the y, I can insert that expression. Great. And then we can solve this to find out what this is. So now we just solve for x. We'll move the x's and gather them on one side. So 2x minus x is x. And then we'll move the 10. So x plus 10 is equal to 15. If we take that away, turns out that it would be the same for 5 movies. So how many DVDs do you need to rent a month for the cost to be the same? For 5 DVDs, the cost would be the same, right? Okay, you would need to rent 5 DVDs. If they went a step further and said, hey, what is that cost that is the same, then all you'd have to do is take that 5, plug it back into either one like we have been doing and get what the cost is. So if I rent 5 DVDs in this plan, 5 times 1 is 5, 5 plus 15, that's $20. And if I rent 5 DVDs on this plan, 5 times 2 is 10, 10 plus 10 is also $20. So when I rent 5 movies, both of these plans would cost the same, which would be $20. Okay. All right, let's try one more and we'll finish off with this one. It says, the senior class at Lake Travis High School and Westlake High School planned separate trips to New York City. The senior class at Lake Travis High School rented and filled 1 van and 6 buses with 372 students. Okay. Westlake High School rented and filled 4 vans and 12 buses with 780 students. Each van and each bus carried the same number of students. So whatever the vans carry and whatever the bus carries is the same. So we want to write an equation that represents the possible combinations for students that ride vans and buses for LT. Okay, so let's talk about LT's equation. X is going to represent the ones that traveled by van, and Y will be our buses. Okay, so let's go back to the sentence that told us about Lake Travis, LT. So LT rented one van, so those are my X's, so 1X, and 6 buses, and that carried a total of 372 students. So that would be our linear equation. Write an equation that represents the possible combinations for the students that rode vans and buses for Westlake. Well, Westlake, let's see, here's our equation. Westlake rented and filled 4 vans, and again, vans are X's, and 12 buses, and they took 780 students. So there's a second equation in our system. Okay, so how many students can a van carry? And so basically what was the capacity for X and what was Y? Okay, so X represents how many kids were in each van, and Y represents how many kids are in each bus. Okay, so we want to be able to use a little bit of substitution here and solve this. All right, so let's go back to our system and take a look at our equations. Nothing's solved for, right? These lent themselves more for that y equals mx plus b, and y was already isolated. On these ones, nothing's really isolated. So I could pick any one of these 4 choices, but this is looking awesome to me. This is sitting here by itself. It's really close to being isolated, so I'm going to isolate that x. Like, you could do any of the 4, but this is the easiest. So I'm going to take this equation and reorganize by moving the 6y, and I'm going to rewrite it x equals negative 6y plus 372. So that's isolated now. It's the same equation, just reorganized. But because I have that x alone, and I know x is equivalent to this expression, I can now take that expression and plug it in where x is in the other equation. So to solve for part C here, our system, I'm going to take this equation 4 times, but instead of writing an x, I'm going to substitute in that 6y plus 372, and then still have the plus 12y and the 780. So I've taken the equation that represents Westlake. Instead of writing an x, I'm plugging in the expression I know is equivalent to x, okay? And we'll distribute and solve. So when I distribute the 4 here, I get negative 24y plus, and when I do 4 times 372, I get 1,488. And I'm sitting here being like, whoo, thank goodness we can have calculators now, right? Well, we don't have to worry about doing that by hand. Okay. All right. And then we combine our like terms. So I've got a negative 24 and a positive 12 here. When I combine those, I'm going to get a negative 12y when I combine this term and this term. And now that everything's simplified and combined, we start to isolate the y. So to get y alone, I'll start off by subtracting this very big number, 1,488, and I'll subtract that from both sides. So that cancels. Now I've got negative 12. Y is equal to 780 minus 1,488. That happens to be negative 708. And then we divide both sides by the negative 12. And maybe these negatives made you a little nervous because it's like, well, a van can't carry a negative number of values, but that's okay because the double negative when we divide cancels and we get 59, which is a very reasonable number of kids riding a bus. So why was the number of students traveling by bus? Every bus apparently contained 59 kids. Okay, and then that takes care of that one. And then we'll plug that back in. So I'm going to throw that back in here up here for x and say, hey, now that I know that y is 59, I can insert that into the equation for x and find out what this is. Well, negative 6 times 59 is 350, I think 54, yeah? And that's a negative, sorry. And then 372, when you combine these guys, x is 18. So every van held 18 students, and every bus held 59. So this is 59 kids per bus and 18 kids per van is what they held. All right. That is word problems and special cases with substitution.